Hello and welcome to the MixOps demonstration series, where you can see live demonstrations for real users and real-world applications. For more information about our products or to schedule your own live demonstration, just give us a call or visit us at www.mixop.com. Without further delay, we invite you to sit back and enjoy the demonstration.
So the next thing we're going to talk about is how to program some of the ring molds or jewelry molds using 3-axis toolpath methods. So I'm going to go ahead and save this file in here, and we'll go ahead and locate another file to work on it for programming a ring mold. Okay, so what I have here is 2 halves of the mold, a ring mold, and the left half and the right half, or you could call it the top and the bottom halves. And I also actually have the ring model in here, as you can tell. So basically you can create your ring design and then do the Boolean operations to create the mold half, 2 halves of the molds. I'm not going to go into the details on how to create the mold halves. I'm sure you're all familiar with it and how to use in your CAD systems. This could be done in your CAD for Rhino. You could be doing it in SolidWorks. You can create these designs, or you could be using any CAD system of your choice, and then you can import those designs into it. So I actually have the ring model and also the actual mold halves. I'm going to go ahead and hide these in the layers. So we'll focus on programming one half of the ring mold in here. So as you can see, the ring mold has been created, and we have the 2 halves of it. So I have these pins and pockets, so it lines up correctly when you put the 2 halves together. So first we'll program the first half in here, the ring mold. So the workflow would be very similar to how we programmed in 2.5 axis. So we would go through the process of defining our machine tool, selecting the post processor, and you want to make sure you establish the orientation correctly in here. So in the next step,
so I just want to interject here. For those people who are very familiar with machining models, wax models, what we're actually seeing, I would like to talk a little bit about the process. What we're seeing, there's molds for creating wax models. So you would create a typical, this is a master mold, if you will, and that's used to create a wax model that you would then put it up in a tree and to create the investment casting. So this is one of the processes that a jeweler would typically go through to create the model, or the master model, or rather the wax model of a jewelry item. So I just wanted to bring that to your attention. Thanks, Uday.
Thank you, Joe. So in this particular part, we have both prismatic features and also sculpted features, where you have pockets with sculpted floors, and so parts like these can be programmed using a combination of both 2 and 3 axis operations. And the first step in here is, again, establishing your machine, your post processor, and then let's go ahead and build a stock in here. So I'm going to go to box stock. We'll do a copy model bounding box. You'll notice that the length, width, and the height have been established in here. I'm going to pick OK to accept it. So I've defined my stock geometry. When you go to the Simulate tab, you'll see that the stock model has been defined. Now, if you're going to be programming this part on the 2 halves on 2 different vices on the same machine tool, you could be using your fixture offsets. You could create a work zero for each of these mold halves, and you can establish them by creating a work zero by specifying set to stock. You could do highest Z. In this particular step, I'm going to pick again southwest corner, and then I'll output this as my work offset number 54, so G54. Now for the other half of the mold, I could be using a G55, which could be my second work offset. So I've established G54 for the first half of the mold, and in the next step, I'm ready to program some of our toolpaths in here. So we'll start with first, pocketing these holes in here. So I'm going to use a 2-axis. I'll start out with just a 2-axis pocketing operation. And I'll pick these face edges on top of these holes. In the next step, I'll make a selection for the tools. I'm going to use a 1/8 inch, which is basically about a 3 millimeter flat end mill. Again, specify feet and speeds and clearance. In the cutting parameters, you can establish your tolerances, cut parameters. Under cut levels, I'm going to choose determine using 3D model, and I'll specify my depth per cut to be 1 millimeter. And leaving all the other parameters at the current default settings, I'm going to pick generate. And we now have a pocket toolpath, and since I chose determine using 3D model, you'll notice that the total depth was automatically determined based off the 3D model, so I didn't have to go and pick the 2 points like we did on the previous example. So you could use determine using 3D model to establish your depth. So now let's go to the simulate tab, and then I'm going to run a verification in here. So I'm going to leave the stock color for this particular simulation in the default color, so we'll apply a different color for some of the other processes in here. Now I'm going to switch back to the program tab and start out with a roughing pass. So I would like to rough the cavity on this mold. So I'm going to use 3-axis and horizontal roughing. Now this method, roughing, is available in all of our configurations, standard, expert, pro, and premium. We'll start by selecting a boundary in here. So I want to contain my toolpath just to the cavity of the mold. So I'm going to pick this boundary. It could be selecting a chain of face edges, or if you have a curve or a sketch boundary, you could select that. Right click or press enter to accept your selections. I'll still go with the same end mill for the roughing process. Establish feeds and speeds, clearance, and then we'll go down to the cutting parameters where you can specify your tolerances, your stock to leave after it's being roughed out, a cut pattern. You can specify in the cut levels, you can specify your step down controls. Engage in retracts can be set under the engage in retract tab. So when you engage in material, when you have cavities, you want to ramp into the cavity, so you can specify the parameters for it. And any advanced cut parameters like arc fitting, perform smooth cut connections. So once you establish these parameters, you pick generate to generate your toolpath. So now the roughing operation has been generated. So I'm going to go to the toolpath visibility to display the toolpath. So as you notice, the cutter was unable to get into some of these tighter areas because the cutter was too large for it. So we would like to go back and reprogram this using a re-roughing operation. Now before I program a re-roughing operation, I would need to run a verification or simulation. So I'll go ahead and assign a color for the simulation. So I'm going to change this to a different color in here for the simulation for the roughing, and then select play to run the verification. So we now have the roughing operation being simulated. Now once the roughing operation has been programmed, I'm going to switch back to the program tab from the simulate tab, and we'll add a re-roughing operation, so horizontal re-roughing. Now the horizontal re-roughing is part of the advanced 3-axis module, which is available in pro and premium configurations. So if you are running standard or expert, you can, if you'd like to get some of the advanced features, you're welcome to call us, and you can find out more about how we can upgrade to the the pro configuration. So for this particular process, I'm going to go over and select a 16th-inch end mill, specify feeds and speeds and clearance, very similar to how we did in the roughing process, and also establish our parameters like the tolerances, stock, cut patterns, cut directions, step overs, cut levels, and engage in retracts. Now the re-roughing operation takes into account the in-process stock, which means the stock that's being left from the previous roughing operation to establish the areas that needs to be roughed. So it's not looking at the initial stock that was defined, it's taking into account the stock that's being left from the previous step. So as you notice here, it's only creating a toolpath where there's material it's being left from the previous process. The re-roughing knows the in-process stock being left from the previous step. So we now have the re-roughing operation programmed, and let's go ahead and run a verification for this in here. So I'm going to pick a different color for the simulation, and we'll select play to run the verification. So you'll now notice that the material is being removed in areas where the larger cutter could not get in. So this is a very efficient way to program it, to reduce your machining time and make your programming workflow a lot more efficient. So once we have the re-roughing program, I would like to go back and program a pre-finishing and a finishing toolpath. So this could be done using a variety of different methods. I'm going to start with a finishing method called horizontal finishing in here, which is also known as finishing in levels. And I'm going to pick this boundary for containment. Now for the tool, I'll pick a taper tool. Again, in this particular step, I'm going to use the 0.5 millimeter 2-degree taper tool for finishing. The feeds and speeds are being loaded from the tool. I'll leave the clearance to automatic and specify the parameters for cutting, the cut direction. I'll leave it as climb conventional, so it'll alternate between climb and conventional between levels. In the cut levels, I can specify my step down. I can use a % tool diameter, or I could even do like a distance, and I can choose the cut level ordering and specify any additional parameters like entry and exit and advanced cut parameters. Having all of this set, I'm going to pick generate. So in this particular process, it's going to generate a finishing in levels toolpath, and there's the Z-level finishing, or also known as finishing in levels toolpath, with a taper ball and mill. So I'm going to switch the simulate tab in here, and I'll assign a color for the simulation. And then pick play to run the verification. So as you now notice, the finishing operation is in progress, and it's creating a pre-finishing or a finishing operation to remove the material to bring the stock as close as possible to the finish shape of the part. So you could be using a combination of different types of finishing methods. You could be doing horizontal finishing, which is offered in all of our configurations, starting with standard, expert, pro, and premium. And you could be using a combination of this with a parallel finishing to achieve the result and the finish quality of finish that you're looking to achieve. Again, at any point of time, you can select pause and hit simulate to end to run through the simulation. Now, as you notice here with the horizontal finishing, since this method is called finishing in levels, as you get to areas that are not very steep, you might not be able to finish all of those areas. So to go back and finish some of those areas, you could be using a method like a parallel finishing in here to clear up material in these areas. So I could go back to the program tab and add a parallel finishing operation. This is also known as planar finishing. Can be great for use for near flat areas or kind of sculpted features. We'll use the same tool. We'll specify the step over in here to 15% of the tool diameter, and then I'll pick generate. So this is also a very commonly used way to finish. Now, if you want to exclude these flat on the top from being machined, you can edit the parallel finishing operation and add this as your containment region as well. So the toolpath will be generated between these two areas. So we now have the parallel finishing operation programmed, and I'm going to go back and run a verification for it again. Again, folks, if you do have any questions during this webinar, you're welcome to post those questions in the questions panel, and we'll try to get them answered for you. Now, once these pre-finishing and finishing operations are complete, we could go back and add an additional toolpath to clean up some of these scallops that are being left around these areas in the part where you see bitangencies on it. So we could be using a method like a pencil tracing or a remachining operation to clean up some of these areas. Now, the methods pencil tracing and remachining are again offered in our Pro and Premium configuration, and those are part of our 3-axis advanced module. So here what you're seeing is the progress of the simulation of the parallel finishing operation. So once this has been completed, I'm going to go back and create a final finishing cleanup operation using pencil tracing. So we'll go into 3-axis advanced, and I'll pick pencil tracing. And again, with the same set of boundary regions selected and with the same tool selected, I'm going to generate a pencil tracing operation in here. And this is going to look at the part geometry and look for all those bitangencies and create a toolpath to go and clean up those areas to result in a nice finish on your mold cavity. So depending on the complexity of the part, complexity of the the type of tool that you're selecting, the computation time could vary from a few seconds to probably a few minutes. So it's doing a lot of processing in here. And there's the pencil tracing toolpath that's being generated. As you can see, it creates a nice path to clean this up. So let's go to the Simulate tab. I'm going to pick a different color in here for the simulation. Now, you could have assigned the colors based off the tool, so I wouldn't have to change it for each and every operation in here. So I'm going to select play, and you'll notice that the pencil tracing operation is cleaning up those areas. So now the mold cavity of the first half is ready, programmed and ready, and it's ready to be post-processed out to your machine. So you can just click on the setup one, right-click, and then select post to post-process this out to your machine. And you could be selecting the post-processor that you'd be using for your machine. In this particular step, I'm going to pick a FANUC controller. I'll just post it right to my desktop. And there's the posted code, and you'll see your G54, the work offset, being output right in here. Now we're ready to program the second half of this mold cavity in here. So I'm going to display the visibility of the mold cavity number 2 and hide the cavity number 1. Now you could be programming this using another fixture offset. It could be like a G55. Now one of the things you could do here is you can group all of these operations what you programmed into a MOP set, like a machining operations set, or you can put it under a different setup. So if you're using standard expert, one of those configurations, you can group these operations for the cavity 1 into a MOP set. So by selecting all of these operations, you can drag and drop them into a MOP set. So when you select the work 0 and MOP set and post it, you're posting the mold cavity 1 with the work coordinate offset. Now I can make a simple copy and paste of the same MOP set in here, do a copy paste. I could do Control-C, Control-V to copy paste, or right-click and copy and paste. And I'm going to insert a new work 0 in here. I'm going to insert a new work 0 after I define my stock geometry for this particular model. So I'm going to go back and define a part box stock in here. Now my stock is defined, and I'm going to add a work 0 for this. So I'm going to click on work 0 and set it to the stock, high Z and southwest corner. And I'm going to pick this as my G55 as my work coordinate offset. Now once I made the copy of this machining operation set, I'm going to place this under the new work 0 as you notice it. So I can reuse most of these machining operations in here to program the other half of the cavity. So I could be programming a roughing operation to machine the cavity on the inside. Now before I program the roughing, I would like to program the areas around these pins in here. So I'm going to start by programming a 2-axis and a roughing operation for that. So I'm going to select these features on the top edge of the pins. I'm going to use that as my part regions, specify the cutting parameters for the 2-axis roughing operation. Under cut levels, I'm going to specify the bottom of cut to be right over here and generate. And that's going to say.
Just a note on the roughing operation, it's a little bit different from the pacing and the pocketing operations in the sense we use the stock model to figure out the extents of the cut. So we automatically figure out the extents and then use any containment regions to stay off of, as you can see here. Thanks, Uday.
Thank you, Joe. So we now have the roughing operation programmed in here. So this is very similar to roughing in 3-axis. However, here, you're using a roughing for 2-axis operation ideal for prismatic parts. And as Joe pointed out, this automatically takes into account the extents of the stock that you defined. In this particular case, it just happens to be a rectangular stock, but if you're using a stock with any other shape, cylindrical or any odd shape, it'll automatically take that into account. So in the next step, we'll go back and program the roughing operation in here. So we'll just go back and reselect this region for the cavity half number 2, generate the toolpath for it. And likewise, repeat the same process for the roughing and then the re-roughing operations in here. So I could go back and I can also specify the parameters for each of these steps. So the roughing operation has been programmed. And now I'm going to go back and program the re-roughing operations by using the same set of containment boundaries in here. Now since I copied and pasted the entire setup of operations, you'll notice that the properties including the simulation, color, the tool, the feeds and speeds, all of them were transferred over automatically. So I didn't have to go through the process of redefine them and recreate them. All I'm doing is dropping the initial set of machining region and then selecting the machining region from the other half of the mold cavity in here. So this would be a typical process of how you would be programming roughing and finishing operations for 2 halves of a mold cavity. And finally, I would be programming the pencil tracing operation as well once I'm through with the parallel finishing operation on it. So this would be for a cavity mold for a ring. You could be working off of a cavity mold for like a pendant, pendant design. So here's an example. What you're looking at is a cavity mold for a pendant design where you have operations like roughing. You have, clear flat tops machining operation to machine all of these flat areas. You could be doing re-roughing operations and finishing using, a variety of different finishing methods. And here what you're looking at is a 3D offset pocketing. So just to give you an example of how you can use a 3-axis methods for programming molds and mold cavities for different jewelry applications in here. Now, we talked about how to program the cavities for the jewelry applications. Now the next thing we're going to go over is how you can actually machine the actual models itself, the ring models itself, using if you actually have the ring design itself and you wanted to see how you can effectively machine these ring models, and we can talk about that in the next example in here, where we'll talk about how to machine these parts, the actual models itself using indexed and continuous machining. Now, before I give you a quick demonstration of that, I would like to hand this back to Chris, so he would like to go over a couple of things in terms of how this can be efficiently programmed in our CAM system.
Before that, I just want to interject a little bit here. Another word on process. So what they just did or showed us was the master mold for maybe a wax model. So this is, you're creating an injection mold that you would create a wax model that we later take it to an investment casting process. So this is the first process that he showed. The process that we're going to show next is actually direct machining of a wax model. You might be able to do that if you don't have a lot of runs of that particular model. If you're doing a one-off or a specialized custom jewelry, you might want to actually directly machine the wax model. So that's what he's going to be showing. So we're not going to be showing, and that's the third application, obviously, which you can cut directly onto metal, gold or platinum, whatever metal you're using. You can use our methods to do that as well, but that's not what we're going to be showing next. So Chris, go ahead. Thank you.
Thank you, Joe. So before we proceed with the rest of the demonstration, we just wanted to quickly review the typical workflow that's used in this process of machining the ring models. So what you see in this slide is left to right a workflow where it's a 3-step process for machining a ring model. So the ring is first laid flat and one side of the part is machined. And then the part is flipped over to machine the other side. And that's the picture that you see in the middle. Once these 2 operations are completed, it's followed by a rotary machining where the part is held vertically. So it's a typical 3-step process. And in order to enable this workflow, there are some specialized fixtures. And what you see on this slide is fixtures that are used for flipping the part over, machining one side, flipping it over, and then machining the other side. And then once, as I mentioned earlier, once these operations are done, the next slide, there are some examples of rotary fixtures that are used for holding the part vertically in order to do the rotary machining. So we just wanted to take a moment to kind of walk through the workflow and the fixtures that are used. And now I'll hand it back to Uday.
Thank you, Krish. So as Krish pointed out, the workflow for machining the actual ring model itself, I'm going to go ahead and show you how we could take advantage of our toolpath methods in our CAM product to efficiently program, follow through this workflow in here. So I have the ring design that we just programmed a short while ago. We did the mold cavities for that. Now we'll actually look at how we can actually program this model in itself. So I actually have the ring, and also if you notice I have one of these fixtures in here for that ring right there. So what you look at in one of the presentation slides, here is a fixture for the ring. So you could be using your rotary axis and index it. You could be machining from the top, rotate it by 180 degrees and program it from the bottom. So in order to be able to machine it from two sides, we need to be able to make sure that the part is fixtured into the stock plank and doesn't fall apart when you're machining from two sides and then putting in a rotary. So we would need to prep the part or prepare it for machining in here. So what we're going to do is I'm going to use a fixture. Now if you take a look at this actual fixture in here, once it's machined on the top and the bottom, the part would get inserted over here on this tip for rotary machining. So that's the reason why I've created this fixture. So once you machine it from the top and bottom for the final finishing, you can line up this part that's finished from the two sides and then put it over to the tip for rotary machining. So we have designed a fixture with the holes that will line up for it. Now once I have this in place...
I just want to interject one more time, sorry. The fixtures that Uday just showed, they're actually from a Roland machine. They come from a Roland JWX line, and we are using the models of those fixtures. So in case you're curious. Thank you.
Thank you, Joe. So you could be using your own fixtures that you may have designed, or you could come up with some standard fixtures you could, obtain. But in this particular example, we'll be using one of these fixture types. And once I have these, designed placed in here, I'm also going to go ahead and create, some support structures to be able to hold on so that the part can remain intact with the stock material. So to create supports, I'm going to use some of the drawing tools in this CAD system in here. So I'll create a boundary in here so that we can contain our tool paths to an area. And also I'm going to add some support structures in here. So I'm going to use simple tools like creating a rectangle in here and extruding them to form supports. So I'm going to model these in here. You could use different types of support structures. I'll use some of the arraying tools in here. I'll do a transform array polar, and I'll basically create 4 of these items. And we now have created some supports in here. I can also go back and make some changes, modifications in here if I need to extend this, make it larger on one of these sides. So I can, you can use your creativity to create supports. It could be intricate, or it could be as simple as what I'm showing here. Now I'm also going to turn this into a solid extrusion by extruding it by solid models. I'm going to use some of the solid modeling tools in here, and we'll just extrude it to a thickness right there. Okay, so we now created the supports for the fixture and actually the part, so that the part stays intact when you machine it. Now the extent rectangle, what you see here is actually the extent of the fixture, the original fixture that we have to be able to play, the stock, so that it can sit inside the fixture right there. So that's what you're looking at. Now let's go ahead and build our stock material in here. So I'm going to click on copy model bounding box, and then I'll put in my material thickness, blank thickness as 16 millimeters. And in this step, next step, I'm going to align it. So use align it to have it centered and centered in X and Y. So we now define the stock and the part, and the supports have been added to it. Now I would like to machine this in 2 halves, like using a flip machining. So I'm going to define my machine tool as 4 axis. And I'm going to use the rotary axis or axis of rotation as X in this particular machine, the Roland machine, the rotational axis as an X axis. And typically also your rotary center and the origin is being left at the center, where the XYZ0 is right in the center of the part. So we've established that. So I'm going to select the post processor in here. I could pick a Roland, or I could pick any of the post processor. Now for this application, I'm going to use the Roland JWX30 as the post processor and output extension to NC. We're now ready to program our toolpaths. The workflow will be very similar to what we did earlier. So the first step is to create a roughing toolpath. So I'm going to use roughing in 3 axes. I'm going to select a containment. So I would like to contain the roughing toolpath to stay up to this inner rectangle in here. And for this particular process, I'm going to be using the 16th inch end mill for the roughing process. Establish the cutting parameters. In a cut levels, I'm going to set my bottom cut level to just slightly stay right up to the mid-plane, or I can go slightly below that by 0.1 millimeter, and then specify engage in retracts and any additional cut parameters, and then pick generate to generate the toolpath. So in this particular step, it's going to create a roughing toolpath. It does roughing in layers or roughing in levels, as you can see it. And now I'm going to go to the Simulate tab to run a verification of it. You could always select pause and then pick Simulate to end to run through the simulation of the roughing process. So once the roughing process is completed, I would want to go back and machine these holes to its through depth, so we don't have to program the holes from the other side. So I'm going to go to 2-axis, and I'm going to use a method called hole profiling to machine those holes. I'm going to pick the hole feature right in here, use the same tool, specify the cutting parameters. I'm going to put in the hole depth, and I'll put in the helix parameters for the hole, and then pick generate. So we now have a hole profiling toolpath for the center hole. It clears it out. I'm going to repeat the same step for the side holes in here as well. So make a copy of the operation, copy and paste it. So you could use Control-C, Control-V. So I'm going to use these holes. And with the same tool, in the cutting parameters, I'm going to choose at bottom. And the hole depth is going to be 3 millimeters and generate it. So the diameter or the size of the hole is automatically determined based on the arc or the circle that you selected in here. Finally, I'm going to repeat the same operation again for the through hole in here. Edit the operation. And I'm going to be selecting the curve edge regions. Again, reselect these edges from the hole. And use the same set of parameters to generate it. So we now have a hole profiling for these 3 side holes as well. So once the roughing operation is completed, if you're working with a manual tool changer, you would want to minimize the tool change. So you could actually do the flip machining for the roughing on the other side as well. To do that, you would go to setup and add what is called a rotate table setup to flip the part over on your rotary axis. And then we're going to put in the table rotation as 180 degrees and then pick OK to accept it. So you'll now notice that the table rotary axis is turned over by 180 degrees on your machine, and you can repeat the same roughing operation in here. So I'm going to copy this over and then paste it under the rotate table setup, so that now the operation is copied over, and I'm going to right click and regenerate. So now the roughing operation is being computed from the other side as well. So let's run a verification in here for the roughing. So you notice that the roughing on the side 1 is completed, so we are simulating the roughing operation for the flip side. You could always select pause and pick simulate to end to run through the simulation in here. So once the roughing operation is completed for both the sides, now it's been completed for the 2 sides, we would want to go back and add some finishing operations. So I'm going to switch back to the Program tab in here. And the most commonly used type of finishing method in here would be like a radial machining operation in here. So I'm going to define a couple of boundaries in here. So I have 2 boundaries that are right on the edge of the part. So I'm going to offset these boundaries about a little over 1.5 millimeters from both the inner and the outer boundaries in here, so that we can have the cutter go past these edges to get a nice finish on it. So after the roughing operation is completed, I would want to go back and add a finishing operation. Now since we've already rotated to 180 degrees, we would want to go back and finish it from the bottom side first. I'm going to use a method called 3-axis radial machining. This operation is available in standard, expert, pro, and premium configurations. So to be able to do the flip side machining, you would need expert or higher configurations. The expert configurations allows you to do rotate table setups and also 4-axis continuous toolpaths. So we're going to be selecting these 2 boundaries in here for the radial machining operation. We'll pick the taper tool in here for the finishing process. We'll establish our cutting parameters for radial finishing. And I'm going to put the center point in here as 0, 0, 0. So that we're going to use a center point for establishing the radial machining toolpath. We'll specify a step over in here, and in the Z containment I do not want to cut below 0.1 millimeter, so I'm going to establish that value right there. So I'm specifying in the parameters in here for the radial finishing, and in the clearance plane I'm going to use a skim clearance for retracts, and then we'll pick generate. So in this particular step we now have a radial finishing operation for the flip side, so the 180-degree side that we rotated from. So I'm going to switch to the simulate tab in here and run a verification for it. So there's the finishing operation for the flip side. So at any point of time you could select pause and then pick simulate to end to run through the simulation. Now once the simulation has been completed on one of these sites, you would do the rotate table back to 0 and generate a finishing toolpath for the initial side, which was at 0 degrees, or the top half of the part. So I'm going to switch back to the program tab, add a new rotate table setup, put the table angle back to 0. So now the part is being rotated back to its initial orientation. And I'm going to repeat the same radial machining operation, do a copy, and then do a paste. So now it's pasted under setup 3, and you see that the operation is flagged as dirty. So I'm going to right click and regenerate it so the toolpath is generated for the rotated orientation. And there's your simulation for the finishing operation from the two sides. So this is how typically you would be programming the flip side machining. Now once the machining from the two sides is completed, you would manually break off the tabs around the outside of the part. So the part would then be ready for tip machining or a rotary machining. So I'm going to let the simulation to run in here by selecting pause and simulate to end. While the simulation is being completed, I'm going to go ahead and show you how we could do the tip machining for the same part. Folks, we're going to be running over this just a few minutes, so hopefully that would be okay with you, so we can make sure that we cover the flip machining and the rotary machining for this ring model we were looking at. So we now have the ring model oriented, and we have the supports from the outside trimmed out, but the supports are still intact on the inside. And this is going to go into the fixture at the tip. As you notice, the fixture, we showed this fixture during the flip side machining. So now you would be placing in a ring with the fixture after machining from two sides over at the tip right over here. So this is how it's going to be, your setup would look like if you're using one of these fixture types. So it looks like the simulation would have been completed over here for the other side. So we have the program toolpaths programmed and simulated from the two sides. Then you can post-process by just going up to the machining job, right-click and post all. Will post both the setups, and it'll output the rotate table setups as well in your posted output file. So it has the output. So this output is for the Roland JWX30 machine. So I'm going to switch back to the rotary machining in here. So we now programmed the part from the two sides using flip machining or using rotate table setups, and now we are ready to program the 4-axis finishing toolpath on a rotary or a tip machining. So again, you define the machine tool as 4-axis, pick your configuration as table, establish your rotational axis and the rotation center in here, and then select your post processor that would be most appropriate for your machine tool in here. So I'm going to pick the JWX30 in here as well, and use NC as the file extension. So to finish these sections, so you would want to finish these because when you machine it from two sides, it's going to leave material in here, so you want to result in a nice finish, so there's an overlap even though you have an overlap, or you may have some additional features like prongs and other features on other ring designs. You would need to go back and do a rotary machining or a tip machining to produce a nice finish of the ring model itself. So to program this, we would be using a method called 4-axis and parallel finishing. So for this process, I'm going to be using the same taper tool that we used earlier, which is a 0.5 millimeter corner radius with a 2-degree taper, and we'll establish the feeds and speeds and clearance. So in this particular step, it's going to be a cylindrical clearance for a continuous 4-axis toolpath. In the cutting parameters, we would establish the global parameters, the stock to leave, and then you can choose your cut pattern. You can either go along the axis of rotation or you could go across. For this particular model, along would be more ideal. And you can specify your cut axial containment, which basically the length on which you want to cut on the x-axis. So in this particular case, it's automatically established this based off the low and the high values are established based off the actual part itself. If you need to extend it, you could always change these values, and you'll see that the preview, the planes on the graphic screens are displayed corresponding to the low and the high values in here. And we want to go 0 to 360, so we want to go around the entire model. So we want to leave the start angle at 0, end angle is 360, and we'll put in a step over in here. I'm going to use 15%. Now under step down, I could specify a radial cut level containment, like a bottom containment, and I'm going to specify this to be at about 8 millimeters. So I want to stop the cutter not going past 8 millimeters. I don't want it to go down to the fixture, so I'm going to put in a cut level radial containment of 8 millimeters in here, and then select generate to produce the toolpath. So there's the finishing toolpath, the parallel finishing 4-axis. We'll switch to the simulate tab and select play to run the verification. So this would result in the rotary or tip machining for the ring model that we just programmed. So you would do the flip machining first, and then remove the, break the supports away from the stock blank and place it over on the tip, and use the tip machining, the rotary machining to program around the ring. So with this, I would like to conclude the demonstration and hand this back to Krish.
Thank you, Uday. Thanks everyone for setting aside the hour to join us today.